it says it's found in both the credit and the DBT schedulers. Okay. So with that background, let me talk about the current credit scheduler and its main weakness. Now, there are several weaknesses with the current scheduler. The first is that it has a very long time slice. If a VM wants to, it can run for 30 milliseconds without being interrupted. It sorts by priority rather than credit. So there's 3 priorities, and one of these priorities is round robin. And it uses probabilistic editing. And this has caused some kinds of problems. But the main problem is actually how it deals with the reset event and how it deals with VMs that aren't using all of their credit. Okay, so let me describe briefly the core algorithm of the credit scheduler. The credit scheduler divides all VMs into 2 categories, active and inactive. So active VMs are actively accounted for. The credit is assigned to them every 30 milliseconds according to their weight. Conceptually, they burn credits at a fixed rate as they run, and there are 2 priorities. Under, which means you have not used up all your credits, you have a positive credit, and over, which means you have a negative credit. And with any under VMs will run before any over VMs, so the strict priority there. But within each priority, it's just round robin. Non-active VMs do not earn or consume credits, and they run it at a higher priority, which is called boost priority. Okay, so we have boost, under, and over. And how do you switch between these 2? So going from active to inactive happens if you earn credit enough to be to some threshold. In this case, it's 30 milliseconds worth of credit. Then it says, obviously you're an IO-bound workload, and you don't need to have the credit. You don't need to have credit count. So resets all your credit, and then now you're in non-active mode, and you run at a high priority. Transitioning from inactive to active happens when you are interrupted by a timer tick. Zen has ticks that happen, just interrupts, that happen every 10 milliseconds. If you are interrupted by one of these ticks, then you will go from inactive to active. So let's consider a VM that's not a CPU burner. It's not using all of its time slice. The problem is that in inactive VM, inactive is an unstable place to be. You are always guaranteed eventually to be hit by a timer tick. So for instance, take our audio VM, which is using 5% of the CPU. There's a 5% chance at any time that the tick will hit the audio VM. So that means that we can expect about, on average, 1 in 20 ticks to hit our audio VM. So since ticks happen every 10 milliseconds, we can expect that the audio VM will only stay in the boost priority for about 200 milliseconds before being switched to active. And when it's switched to active, its credit set is set to 0, and so it will immediately be debited credits. So it will be an over. The over priority is very low priority. We slowly earn enough credit to be in under priority, but even then, it's being scheduled round robin with all kinds of other VMs. And eventually, it will earn its way up to 30 milliseconds worth of credit again, and be reset down to 0 credits, but be in the boost priority. So we can see that any VM that is not using 100% of the CPU as allowed will flip back and forth between active and inactive. And every time it goes to inactive, it will immediately be put at the bottom of the priority and have to slowly earn its way back up before being flipped back and forth, before being allowed to run a boost priority. So for credit 2, the reset condition is one of the core design points of the algorithm. So here's the basic description. All VMs start with, or all vCPUs, start with the credits at some fixed value. Okay? VMs burn credit at a different rate depending on their weight. So a VM with a lower weight will burn faster, and a VM with a higher weight will burn slower. And you're always inserted into the run queue based on your credit. So you're always sorted by the amount of credit that you actually have left. And the reset condition is this. When the credits of the vCPU at the front of the run queue is less than or equal to 0, then we reset everybody's credit back up to the starting point. This discards everybody else's credit. And because of this, because everybody's credit is reset, there's no sorting required for the run queue. So as a slight refinement, and I'll show you kind of the next picture, hopefully this will make a lot of these things clear. There's a clip and add. So instead of just resetting everyone's to some fixed value, like 500, we'll clip everyone's to, if you have more than 50, then you set down to some fixed value like 50, and then you add 500. And this allows you to, it allows the scheduler a little bit of flexibility. It allows you to let the VM run longer and run into negative credit. And it also allows VMs that are not using all their credit, but are still very latency sensitive, to be automatically at the front of the run queue next time they run. Okay, so here's an example we have here. The x-axis is time. The y-axis is amount of credit left. Okay, and each of these different lines is a different VM. Now, I should emphasize this is actually run in a simulation. This is implemented in real Unreal system, but I haven't had time to take a trace and pick around. So this is a graphical simulation. As you can see, the blue one at the top there is our audio VM. It's when the line is flat, that means it's not running, and when it's at an angle, it is running. So the audio VM there at the top, it's running for a very short amount of time, every 200 milliseconds. And the other lines we have here are other different workloads, some of which run for long periods of time, and other ones which run for short periods but very frequently. And yeah, so as we can see, this line here in the middle is the reset condition. So the VM, whatever the VMs at the front of the run queue were negative, and so we reset everybody. The thing is, so what the reset condition does is it divides things into kind of epochs. And within each epoch, each VM will get the amount of time, its kind of fair share according to the weight. And so the overall effect is that it also gets the fair share. Okay. Right, so now more technical stuff. A couple other changes that I'm planning on making. Right now that we have one run queue per thread. And the reason for that usually is because you want to do an explicit vCPU migration to avoid the cache problems. But in modern processors, many cores and all threads share the same L2 cache. So what I decided to do is, because they're all sharing the same cache anyway, I wanted to have one run queue per L2 cache, so that all of the so any of the threads on that cache can pull from the same run queue. So this may mean that an individual vCPU may migrate very frequently between threads. Because it's all in the same core, that should be okay. Okay, early results, audio is better, it was great, and the network is much more fair. I'll have to speed up a little bit here, so I'm going to rush through the rest of these. Load balancing may only do that between L2 run queues, and so I plan on making it much more explicit load balancing based on historical load. A bit more similar to the Linux scheduling domains hierarchy, if anyone's familiar with that. Hyperthreading, one of the advantages of the algorithm that I've described here is that because we burn credit at different rates already, we can also change the rate at which you burn credit based on what the other thread has been doing. So this will allow us to fairly